All right, so hopefully you have written down this little chart on your paper, okay? So if you ever get like real freaked out about this notation, like you're not like, I don't want letters, remember you can just always plug in numbers if that makes you feel better, okay? So you can plug this into your calculator and then you can actually see what happens. But for your domain, when your A is positive, that means that this number right here is positive. Your domain's going to be whatever your H value is all the way to the right. So it's going to be H value to positive infinity. Notice how I used a bracket on this side and a parentheses on the other. For your range, it's going to be what your K value is, or this 4. So it's going to be from K to positive infinity. Okay, so when your A is positive, that means this number that's up front is positive. This is how it's going to be written. And again, obviously you would have numbers plugged in there. When your A is negative, so that means that you've got y equals -2, then what's going to happen is you're going to have your domain kind of flip-flop. So it's going to go from negative infinity to your H. And that's a bracket over here. And then your range is going to go from negative infinity to K. Okay, and again, you can plug that into your calculator and always check it. Okay. For your cube root functions, it doesn't matter if you're positive or you're negative. Your domain and your range are always going to be negative infinity to positive infinity for both of these. Okay, so if it ever has like a little thing, a little 3 chilling in that little cubby hole, not out front, but actually in that little cubby hole, then it's a cube root function. Okay? All right. So after you've gotten that copied down, I want you to go ahead and take a moment and look at this question over here. Okay? It says the water is draining from a tank connected to 2 pipes. Okay, so I'm a visual person, so I always like to draw this stuff out. So I got a tank and it's connected to 2 pipes. Okay? And the speed, F, in feet per second at which the water drains through the first pipe can be modeled by f of x, right? So this is the first pipe, okay? Where x is the depth of water in the tank. Okay, so x is the depth of water in the tank. What is the domain of the function? Okay, so you can do this either of 2 ways. You can take this function and plug it in Desmos, because if you're unsure of what this point is, that might help. Okay, or you can look at what your h value is, which is 2, and it goes over to the right? So it's positive infinity. So just like what we did over here, we did h to positive infinity. Now it does say interpret the domain in context. So remember, domain is our x values, right? And our x value, as it says up here, x is the depth of water in the tank. The depth of the water in the tank. Okay. So this starts at 2 and then goes on to infinity. But it's draining, right? So we're also talking about this function right here is talking about this pipe. Okay? And x is the depth of the water in the tank. Okay, so we have to keep that in mind. So the starting depth is at 2 of the water in the tank. Okay? Okay, so looking at that second problem, I'm going to change my color. Look at this pink color. Okay, so looking at my second problem, it says a function f was transformed resulting in the function below. What is the domain of the function? So looking at my x value, my point starts right here, right? Now this line is going up by 2's, right? And this point is kind of like almost 6, but not quite, right? Let's get rid of my pink. It's like almost 6, but not quite. So it's kind of in the middle. And so in between 4 and 6, there's the number 5, right? Okay, so with that being said, our domain is going to be negative infinity, because this is going to the left, right? Negative infinity to 5. Now, how does this compare to the domain of the parent function? Okay, well, let's think about it. Remember, our parent function is the square root of x. So this obviously has a negative out front, so it's flipped. So looking back over here, our domain is now flipped because our a is less than 0. Okay, so that's something to keep in mind. Okay, so our domain is flipped because a is less than 0. Okay, it's also shifted to the right. Shifted to the right. Okay, so when we talk about those transformations, remember you're talking about that h and k, and your h moves left and right, right? Right here in our parent function, our h and our k are both zeros. Okay, so instead of it being 0, it's now 5. Okay, so looking at this one, it says Adam found the restricted domain of a square root function. His work is shown. Do you agree or disagree with his conclusion? So on this one, remember, our k value has nothing to do with our domain. Okay, so our k value has nothing to do with the domain, so we really could like ignore that guy, right? Okay, so we're going to take this, set it equal to 0. Ooh. Okay, and then we're going to square both sides because we're wanting to get rid of that square root. I need to make this bigger. Hold on one second. Cool. Yeah. Oh yeah, there we go. Okay, then we're going to divide by negative 1/3. So I've got x minus 5 equals 0. And then we're going to add 5. So x equals 5, right? So we've got from negative infinity to 5. Another way to say this is to say x is less than or equal to 5. So these are the same things, okay? You might see one of them written on the SAT one way, and then you might see this on most of our tests. But you need to make sure that you know both notations. Okay, so he did do it right, so we do agree. Okay, and another way to actually check him and make sure that he was doing it right is that if you go into your Desmos calculator, and you look at the graph, look at where it is. We got here all the way to negative infinity, right? Okay, so going back to our document, that's exactly what he wrote right here. Okay, so Adam did do it right, and that's because everything that's underneath the radical actually deals with your domain. Okay? Tommy visited the Museum of History and Technology with his class. They saw Foucault's pendulum in Pendulum Hall, and it was fascinating to Tommy. He knew from science class that the time it takes a pendulum to complete a full cycle or swing depends on the length of the pendulum. The formula is given by that. where T represents the time in seconds and L represents the length of the pendulum in feet. He timed the swing of the pendulum with his watch and found that it took about 8 seconds for the pendulum to complete a full cycle. Help him figure out the length of the pendulum in feet. So Tommy thought that the pendulum took a full 20 seconds to complete a full cycle. It would be very dramatic for a museum. How long must that pendulum be? If the ceilings in the museum are about 20 feet high, would this pendulum be possible? Okay, so really quick, let's start here. Let's start with, because these are two different type questions. Okay, so up here at the top, it says that we've got T equals 2 pi square root of L of 32. We know T is 8, so we're going to take 8 and we're going to plug it in, right? And then we want this square root by itself. So like back when we were solving, remember that first step is to isolate the radical. Okay, so we're going to divide by 2 pi on both sides. And so that's going to give me square root of L over 32 equals 4 divided by pi. I'm just going to keep it like this. If you plug this in, you're going to get a decimal. I personally don't like decimals. I like keeping it in fraction form. And then you're going to square both sides. So our second step was to square both sides or cube it. Okay, so that'll give me L divided by 32. And when we square 4 divided by pi, we're going to get 16 over pi squared. And then we're going to multiply by 32 on both sides. Okay. And when we do that, we're going to get we've got 16 times 32, which is going to give us 512 divided by pi squared. So pi squared, 3.14 times 3.14. Ooh, nope, let's fix that. 3.14 times 3.14. That's going to give us roughly 98596. So the length is actually going to be L equals 51.9 in feet. Okay, so you got a 51.9 foot long pendulum if it takes 8 seconds for it to complete that cycle. Now, Tommy thought that a pendulum took 20 seconds to complete a full cycle would be very dramatic for a museum. How long must that pendulum be if the ceilings in the museum are about 20 feet high? Would this pendulum be possible? Okay, so if L actually was 20, how long would it take? I'm sorry. Yeah, so if you had a height of 20 feet, how long would that take? So let's think through this. So if I have T equals 2 pi square root of 20 divided by 32. Okay, I'm going to go into my calculator and literally type this in. I'm going to go 20 divided by 32. And then I'm going to take the square root of it. Okay, and then I'm going to multiply it times 2 times pi. So that's going to be T equals 4.96 seconds. Okay, so if it was a 20-foot pendulum, it would take 4.96 seconds. But his question was, if you had a 20-second pendulum. So instead of plugging 20 in for the height, we're actually going to plug 20 in for the T. Okay, so I did plug in 20 for T, and I got 324. So if you pause the video, you can actually look at this work. But it would not be possible if the ceilings were 20 feet tall. So that's how you do it. And if you have any questions, just contact your teacher.